Hi everyone, I'm going to start chapter 7 in this lecture, which is about multimedia networking. Here is a quick outline of this chapter. In the first section, I'll talk about multimedia networking applications. Then we focus on streaming stored videos and how uh, we can handle such a streaming in an efficient way. In section 3.7, we'll talk about voice over IP techniques. And finally, in the last section, we talk about network support for multimedia. As you know, the audio is an analog signal, and the question is how we can store audio digitally. And to do this, the first thing we need to do is called sampling. We have to divide time into equal size time intervals, and for each time interval we have to find the audio signal amplitude. And for example, in this time period the actual analog signal looks like this, the blue line, the blue curve, but we have to do sampling. By sampling I mean divide every second to n different samples. The n is called sampling rate. So if you divide 1 second into n pieces, that means the sampling rate is n samples per second. And then in order to specify the value of signal amplitude in each of the samples, we have to use a quantification method. For example, they usually divide the amplitude values into 256 different discretized values, and based on the amplitude, the value of the amplitude, we choose one of those 256 values from 0 to 255. And then for sampling rate, depending on the application, we choose different values. For example, in telephone, because we don't need a lot of quality, we can use only 8,000 samples per second. However, for a CD music, which we need a higher quality audio, we can set the sampling rate to 44,100 samples per second. As I said, the analog value of each sample has to be quantized into 256 different values, and that will create some quantization error. Look at this red line segment. As you see, the quantized value of the analog value is different from the real value of analog value, so the difference is quantization error, but the error is not that much, and we can handle it. We can, no one can feel such value, error value in the audio quality. However, if you want to minimize this quantization error, we have to increase the sampling rate. So the question here is, how much memory do we need to store 1 second of either music or telephone audio? For telephone audio, because the sample rate is 8,000 samples per second, and each sample can have a quantized value between 0 to 255, so we have 256 quantized values per sample. So if you do a quick calculations, we need 8 bits for those 256 quantized values, because 2 to the power 8 is equal to 256, and the 8 has to be multiplied by the number of samples per second, which is 8,000, and the result is 64,000 or 64 kilobit per second. That's the amount of memory that we need for storing 1 second of an audio with 8,000 samples per second. Now, if you want to increase the quality, for example, for CD quality, we need to increase the sampling rate. So the 8000 will be increased, and therefore the amount of memory that you need for storing 1 second of audio in CD quality would be much higher. So in this case, after some calculation, you can figure out that uh, for having CD quality, we have to have a 1.411 megabit per second memory, and then if you want to have MP3 qualities, we have different memory rates or storing rates. But as I said, for internet telephony, we don't need that much of high quality. So 5.3 kilobit per second and up is the normal rate for internet telephony, which is much less than MP3 or CD. For videos, we also have a similar discretization technique. The reason is that video signals are also like audio signals that are continuous by nature, but the computers cannot store continuous signals. It has to be discretized first, and then computers can store it. So therefore, we have to come up with a discretization techniques for video data. So the technique has two different layers. One layer, which we call it temporal layer or temporal coding, will divide every video into 24 images per second. And the second layer, which we call it a spatial coding, will divide or will model every image into an array of a two-dimensional array of pixels, and every pixel can be represented by a number of bits. There are some techniques both in temporal layer and spatial layer that can decrease the number of bits used to encode the video substantially. For example, in spatial coding of this image, instead of sending n values of the same purple color in these rows, we can simply send two values, the color value, which is purple, and the number of repeated values. So this way we can decrease the number of bits used to encode the image substantially. Also in the temporal layer, we have some techniques to save some memory. For example, if you assume that this image is the next frame after this image, so this image is frame I and this image is frame I plus 1, then instead of sending the complete frame at I plus 1, we can only send the differences between this frame and the frame before, since frame I and I plus 1 are recorded in a very short time interval, so there would be a very small difference between these two frames. So instead of sending the complete frame at I plus 1, we can only send the tiny differences that it may have with frame I in most cases. We can have a constant bitrate for either the spatial coding or temporal coding, and also we can have a more smart technique, which is a variable bitrate, in which video encoding rate changes as amount of spatial and temporal coding changes. So for example, if you have a very steady scene and it doesn't change very often, so for temporal coding you don't need to have a huge bitrate. Usually it would be very small, but if you have a very active scene and everything is changing in the frame, then the temporal coding should be increased substantially. So it's a much smarter way of discretizing videos. In order to compare the video bitrates with the audio bitrates that we saw before, you can see these numbers. For MPG1, which is CD-ROM, we need 1.5 megabit per second. For MPG2, which is DVD quality, we need 3 to 6 megabit per second. For MPG4, which is often used in the internet for streaming and other purposes, we need less than 1 megabit per second. Generally, there are three different types of applications that use multimedia networking. The first one is streaming the stored audio or video. We call it a streaming because you can begin playout before downloading the entire file, and then the video and audio are stored at a server because the server can transmit faster than the audio or video rendering speed, and therefore it's possible that the client play a video that is stored originally at the server, and then it needs some techniques like storing and buffering in the client side. There are many examples like YouTube video streaming, Netflix video streaming, or other applications that we usually use for watching movies or TV series. Another type of applications are conversational voice or video over the IP protocol. Because of the nature of human-to-human conversation, these kind of applications cannot tolerate a lot of delays, because then you cannot have a normal conversation with a lot of delays. So that's a big challenge of such kind of applications. As an example, you can consider Skype. And the last type of application, but definitely not the least, is the streaming live audio video applications, which is increasingly more popular now than before. And you can have many examples of such streamings. For example, when you have a live sporting event, the best way to watch it is to use live streaming. Here you can see a plot of how cumulative data changes over time for recording, sending, and playing out a video in the client side for a streaming a stored video application. Obviously, this is a very simplified scenario. As you see in this figure, we have three different plots. The first plot, which is shown in black color, is the plot of how video is recorded over time. For example, the video is recorded 30 frames per second, and then after video is recorded and stored in the server side, the server sends the video over network. This is the rate that this video is sent or transmitted through the network. And then after some delay, in which we assume that in this case we assume that the delay is fixed, but in reality it's obviously not fixed. After some time, we have this blue plot that shows how the video is received over time and played out at the client side. In this example, as you see, the rates in which the video is recorded, the video is sent, and the video is received and played out are all equal. As I said, this is a very, very simplified and unrealistic scenario, but that's a good first step toward understanding how streaming stored videos work. And as you see in this moment in time, while some parts of the video are still being sent from server to the client, the initial part of the video is getting played out by the client. So we have some moments in which we have both video sending and video receiving on both sides of the application. Having a streaming stored video over the network has a lot of challenges. The most important constraint that exists in such applications is that uh, we have to have a continuous playout on the client side, which means once the client starts watching the video, then the playback has to match with the original timing, but it's not very easy to do so because the network delays are variable, and they are dependent on many factors like network congestion, and that may cause jitter on the client side. So we need some client side buffering to uh, eliminate or minimize the possibility of jitter in order and match the playout requirements. There are some other challenges. For example, a client wants to have interaction with the streaming video. For example, if he wants to, or she wants to pause it or fast forward it, rewind it, jump through a specific moment in the video. So these are all the challenges that makes streaming very hard, because if someone wants to jump to the middle of the video, uh, you have to wait a long time before all the video is sent from the beginning up to the point that you want to jump to it, or you may need to use some more complicated protocols for streaming videos. And then as you know, the video packets, like other data packets, may be lost, and then if we use, for example, TCP, you have to retransmit those lost packets, and that causes variable delays, which is very challenging for continuous playout constraint. In this figure, we see a much more realistic scenario of how cumulative data changes over time for transmitting data and receiving data in the client side and playing it out on the client side. So basically, the red plot shows the rate of video transmission by the server. As you see, the rate is constant in this case, and after the video is transmitted from the server side, in the receiving side, in the client side, the video is received in a variable rate. As you see, the reason is the network delay is variable for different packets that is transmitted through the network. So for example, some packets like this one is transmitted with a longer delay. However, a packet like this one is transmitted with a shorter delay. So this is how the realistic scenario looks like, more or less. And then when the client receives the video, he or she doesn't play it out immediately. The playout delay, there's a playout delay of this much, as you see, for a client to play out the received data, the received video. The reason of the playout delay is to compensate for network added delay and minimize the chance of jitters, and in order and to keep the continuity of playing out the video. And finally, you see the blue plot that is which shows the rate in which the video is play out at the client side. Obviously, this rate has to be constant because the client wants to enjoy the video, and it has to be rendered in the same way that the video in the same rate that the video was recorded, so that the video looks natural. At any point in time, the vertical difference between the blue plot and the black plot, as you see in this case, in this time, this difference shows how much video is buffered, and this value of buffered video varies. As you see here, we have this much of buffered video at this time, we have very little buffered video. If this buffered video reaches to 0 or it becomes negative, then we have uh, jitters, and the playout would not be smooth and continuous. So it's better to increase the playout delay in order to avoid jitters. But on the other hand, if you increase it a lot, then the client has to wait a lot before watching the video, which is not very pleasant for the one who wants to enjoy a video. Here you can see the buffer of the client side as a system. Look at this figure. As you see, when a server sends a video through the internet, it will be received by the client with the variable rate of x of t. That's why we show it by x of t, because it's a function of time since it's variable. But when the client receives it and wants to play it out, the client uses a constant rate because we want to enjoy the video with the original rate. So we have to have the constant rate of r, for example, and then the buffer is like a system that gets some input flow of data with the rate of x of t. That's the rate in which the buffer is filled, and the output rate of data, which is the rate that the buffer is emptied out when you play out the video. So since we consider buffer as a closed system, the buffer fill level, which is specified by q of t, is also variable, and it can be calculated by the integral of the input ratio, or the input flow of data, which is x of t prime, minus the output rate, which is r, d of t prime, and then the integral should be from the time we start the process, which is 0, all the way to a certain time, which is t. So if you take this integral, you can get q of t as a function of both x and r. So if you consider some playout delay in the client side, for example, if assume that the delay is t of p, which means the playout will begin t of p after the first packet of video is received, then the initial buffer fill level when the playout begins should be equal to the integral of 0 to tp x of t d of t, because there is no playout rate from time 0 to t of p. Therefore, you can simply calculate the buffer fill level, or it's better to say the initial buffer fill level before playing out the video. After time t of p, the buffer fill level will vary too, but it would be good that we have some buffer fill level initially, so that we can reduce or eliminate the chance of having jitters. Here, let's consider a new quantity, which we call it average fill rate. As I said before, the fill rate is variable for the buffer, because the network delay is variable, so the rate in which the video is received by the client is variable. So this function of time, x of t, has an average over time.
So let's assume that the average is represented by x bar. So x bar is equal to the average of x of t, which can be calculated by this integral divided by the time that we are considering the whole scenario, the total time. And if you rewrite the formula for q, then the q of t can be simplified to this integral minus r times t, where t is the total time that we consider the average over it. So based on this formula, you can replace this integral by t times x bar, and when t times x bar is replaced, you have q of t is equal to t, t is factored out, t times x bar minus r. So as you see in this formula, if x bar is less than r, then the number in the parentheses would be negative. Therefore, the q of t becomes negative. Since the buffer fill level cannot be negative, that means the buffer will eventually be emptied out, and then that causes freezing of video playout until the buffer fills again, and we can come back to the normal situation. But in the case that the x bar, which is the average fill rate, is greater than r, which is the playout rate, the constant playout rate, then everything is okay. The buffer will not be emptied, and the reason or the way that we can provide this situation, this favorable situation in which x bar is greater than r, is to have a little bit of initial playout delay. This way you can increase the x bar so that it become more than the playout rate r. But as I said before, there's a trade-off for the value of initial playout delay. If you make the delay very much, then it would not be pleasant for the user to watch the video, and if you keep it too small, then you have a lot of buffer starvation. In order to have a streaming multimedia, there are different options for the transport layer protocol. One is to use UDP. In this case, server sends at an appropriate rate, which is usually equal to the encoding rate and the constant rate for playing out the video. And then, obviously transmission rate can be different if we have different congestion levels in the network. And, the playout delay is usually between 2 to 5 seconds to remove the possibility of freezing. Also, since UDP doesn't provide reliable service, then you should have error recovery in the application level, not in the transport layer. Another problem that can raise while using UDP is that UDP may not go through some firewalls. On the other hand, there are some multimedia applications, streaming applications that use HTTP and obviously TCP for the transport layer. So in these applications, multimedia file is retrieved via HTTP GET, and the server sends at maximum possible rate under TCP. So this way we have in-order delivery, but we may have a lot of retransmissions, and the fill rate might fluctuate because of TCP congestion control. And we usually need larger playout delay to make the TCP delivery rate smoother and absorb the fluctuations of fill rate by the playout delay. And then Another difference that this kind of applications have with the UDP streaming is that HTTP/TCP passes more easily through firewalls. A smarter way of streaming multimedia is to use DASH, which stands for Dynamic Adaptive Streaming over HTTP. This is a protocol that is much smarter than the normal HTTP/TCP. Basically, the server in this kind of protocols divide the video file into multiple chunks, and each chunk is encoded at different rates. That will be explained why we have to encode chunks in different rates, and then server sends a manifest file to the client. The manifest file basically provides the URL for each chunk of video, and obviously the client has to order each chunk from the appropriate URL. The client side, after receiving the manifest file, has to periodically measure the server to client bandwidth, and based on the bandwidth at the time, the client has to request one chunk at a time, and for that chunk, client has to choose the maximum possible coding rate that can be received given the current bandwidth. If the bandwidth is very high, then the client can obviously ask for a larger coding rate than when we have a congestion in the network and the bandwidth is poor. So in such situation, the client can only ask for a low quality chunk of video. In any case, the coding rates are different depending on the available bandwidth. So in the Dash protocol, the client is the one who decides when to request a chunk and what encoding rate to request, and where to request a chunk, because sometimes a chunk can be available in different URLs, and the client has to decide which one has a higher available bandwidth to choose. Another challenge in this kind of application is to stream single content to hundreds of thousands of simultaneous users. The first option is to simply choose a large mega server, but this option is not sustainable because you have a single point of failure. If the server fails, then everyone else, all the users cannot watch the video, and it has a network congestion problem because there's a lot of traffic on the lines that are close to the mega server, and there would be a long path to the clients that are distant from the server, and that cause a lot of problems for video streaming, because the network delay would be substantial. And obviously this is not a smart solution because we are sending multiple copies of the same video over and over and over on different links. So there should be a much more efficient way to broadcast video in these cases. The simple solution to this problem is to store multiple copies of videos on multiple geographically distributed sites, and this way we have distributed servers, and then they can serve thousands and thousands of clients in a much more efficient way, because this way the clients can choose from different servers, and at each time they can get a chunk of video from the server that is closer to them and has a higher available bandwidth.